Okay, so we're going to intro a little bit of 6.3, which is binomials, which is a specific type of probability problem. We have binomials and geometrics, and then we will wrap up the probability unit. So let's just kind of look at a problem to go through this. So in the 2005 Conference USA basketball tournament, Memphis trailed Louisville by 2 points. At the buzzer, Memphis's Darius Washington attempted a three-pointer. He missed but was fouled and went to the line for 3 free throws. Each made free throw is worth 1 point. Was it smart to foul? So kind of looking at this in all the steps, the first thing is what are all the possible ways the shots could fall? So basically what they're asking you for is your sample space here, right? And so my sample space is going to be that I could have made them all, right? That's one possibility. I could have made the first two, missed the second one. I could have made the first one, missed, made it. I could have missed, made it, made it. Now I get into only making it one time. So I could have made it on the first one and not the second two. Made it on the second, not the second and third. Made it on the second one only. Made it only on the third one. Or I could have not made it on any of the three. And so that is those are basically my 8 possible outcomes. And so now let's learn a little bit more about Darius Washington then. So Darius Washington was a 72% free throw shooter. Find the probability that Memphis will win, lose, or go to overtime. When you have found the probabilities, put them in the table in number 3. Okay, so again, he was attempting a three-pointer. Okay, and Memphis was trailing Louisville by 2 points. So to win, he needed to make all 3 of them. To tie, and so that they would go to overtime, he would need to make 2 of them. And they would lose if he made 1 or less. So the only possible way that they can win is by him making all 3 of them. So this combination right here is the only possible way that he can win. Okay, and we would assume that these are independent of one another. So I am going to have 0.72 to the third power, or 0.72 times 0.72 times 0.72, which is going to be 0.373. That is the probability now that they would win, because he would have to make all 3 for them to win. The probability that they lose would be that he doesn't make any of them. So this one right here, okay, where he doesn't make any of them, or he doesn't make 2 of them. So any of these possible combinations here. So there's one combination where he doesn't make any of them. Okay, well, if he's a 72% free throw shooter, the probability that he doesn't make it is 0.28. Right? So the probability that he doesn't make all 3 is going to be 0.28 to the third, which is going to be 0.022. Right? But then he also could have 1 make and 2 misses. Right? And so he has 1 where he could make it, 2 times where he misses it. Right? And that probability is 0.056. But you have to remember there are 3 possible ways that he can get that. So we need to combine those together. Right? So now I need to take this and I need to multiply that by 3, which gives me 0.168. So now I can combine my 0.022 with my 0.168, and I would get my probability that they end up losing. So let's kind of come out here to the side and finish that up. So 0.022 plus 0.168 gives me a 19% chance that they would lose. So a 0.19 probability that they would lose. Now, if I wanted to see if they would go into overtime, overtime is 2 makes and 1 miss. So there are various combinations of those. Okay, and so basically that's this chunk right here. But if I have 2 makes and 1 miss, that's 0.72 times 0.72 times 0.28, which will give me 0.145. But again, there are 3 ways that I can do that. So when I then multiply that by 3, I get a 0.435 probability that they would tie and send it to overtime. And so the official formula for how you would calculate that is on your formula chart. And we're going to break it down a little bit right now to kind of look at what's happening with that formula. So if you look at the formula looks super crazy. It's if x has a binomial distribution with the parameters n and p, and then it gives you all the awesomeness that is your formula. So your formula looks like this: n, x, parentheses, and then p to the x times 1 minus p time to the n minus x. Oh, what a mess. Okay, so this is what your formula looks like. So let's look at the pieces of the formula and how these things fit into this formula. So when I'm looking at this formula here, okay, n would be my total number of shots as it applies here. X would be my shots that I'm going to make. Okay, P is my probability that I make them. 1 minus P is my probability that I don't make them. Okay, and again, N was my total shots and K was my makes. Right, so if we, let's look here. So in this particular example, right, these are my yeses, these are my makes. I'm sorry, back up. Those are my totals. Got ahead of myself. N is my total, right? Sample size. This is my total shots that he's going to take. X is going to be what we want, which is how many he makes. P is my probability, right? Or my percent make, right? My decimal. Okay. 1 minus P is my miss, my probability of missing, right? N minus X, again, is my total shots minus the makes, which would be how many we would miss, right? So if we look at this, in this particular example, okay, what this looks like in your calculator is you will, and I think you guys maybe have seen this in your math classes, that's what you would use in your actual calculator instead of, you can't use this part right here that's in parentheses. So if you have your calculator with you right now, and we'll look at this in class as well, if you go to math, arrow over to prob for probability, arrow down to number 3, and you get NC, and in your calculator it's an R. Okay? And you hit enter. And now you can put in your N and your X values. So in this particular example, what went into my calculator would be 3, because that's my total number of shots, right? This is my N. He has the opportunity to take 3 free throw shots. C, and then my R here is 2. This is how many, in this particular case, it's how many he would make. And then I'm gonna, so that takes care of, on our formula, that takes care of this part right here. So now I need to multiply that. I'm gonna use the dot for multiplication, times my probability that he makes it. So he's a 0.72. And how many he needs to make? He needs to make 2 of them. And then I multiply that by the probability that he's going to miss it, which is 0.28. Right? So here is the make. Here is the miss. Again, this is my X. The probability he's going to miss it, raised to the 3 minus 2, or 1. Right? How many he's going to miss, basically. And then when I hit enter in my calculator, I get 0.435. So the formula looks a little crazy, but when we remember what it means, it's not so bad. So again, N is my total. X is how many I get, is I do the thing that I want to do. In this particular case, I want to make free throws. P is the probability I make them. 1 minus P is I don't. And N minus X is how many times I don't get a success. When we do talk about these, a lot of times we call these a success. So let's dig a little bit deeper into this problem. I'm going to erase all this stuff, so if you need to, pause and write anything down. Okay, so let's look at part 3 now. So prior to watching each shot, calculate the probability that Memphis wins the game in regulation, loses the game in regulation, or sends the game into overtime. Okay, so we're actually just going to kind of take a look at what actually happened. So the probability that Memphis is going to win, we already calculated that, right? It is 0.393. The probability that Memphis will lose, we also already calculated that in green above. That was 0.191. The probability they will go to overtime, we also calculated 0.435. So all of those should add to 1, right? It's a good distribution. So here's the first 2 columns are our score, right? Memphis was at 73, Louisville was at 75. So he takes the first shot, and now he makes it. The score is 75-74. So now for them to win, that probability for them of them winning is going to change now, because now he just needs to make 2 in a row. So now our probability, this is like the card problem, right? I didn't return the card. So now I only have 2 left. So this is now my probability that I'm going to win is 0.5184. My probability has changed. Okay, now my probability they lose is he's got to miss both of them. So 0.28 squared, 0.28 times 0.28. So very low probability he's going to miss both of the next 2. Okay, and then our final probability they go to overtime, he's already made the first shot. So now he needs a miss and a make, or a make and a miss, right? Either way, he needs to miss 1, make 1, or make 1, miss 1, doesn't matter, right? But then he needs to multiply that whole thing times 2, right? Because it could go either way. So 0.4032. So that's his new probabilities now. So now he takes his second shot, right? So he takes the second shot and he misses. So they're at 74-75. So the probability Memphis can win now is 0. He only has 1 shot left, so they cannot beat them. The probability Memphis loses now changes to 0.28, because what if he misses? And the probability that they go to overtime and he ties it is 0.72, that he's going to make this shot. Okay, so Washington is a 40% three-point shooter. Do you think Louisville was smart to foul? Well, what ended up happening was he ended up missing that last shot, and Memphis ended up losing. So if Washington is a 40% three-point shooter, do you think Louisville was smart to foul? Okay, so again, he was lined up to take the three-point shot, and he's a 40% three-point shooter, and they would have won the game if he'd made it. So at that time, they had a 40% chance of winning. Memphis had a 40% chance of winning, 60% chance of losing, which means Louisville had a 60% chance of winning and a 40% chance of losing. Louisville fouled them. Okay, so in fouling them, when the free throw thing started, Louisville had a 0.191% probability of winning, and a 0.435 probability of ending up going to overtime. Okay, so together about a 0.5, 0.6 probability of winning or going to overtime. So do you think it was good for them to foul? Maybe. The chance of losing in regulation goes down. Okay, so as he continues to miss free throws now, the chance of losing in regulation goes down. But they could have had to go to overtime, and so they could have lost there. So this one isn't isn't like a huge difference between the probability of them winning based off his 3 free throws or his shot. He just was, I guess, having an off night, and he missed those last 2 free throws. Okay, so our takeaways here. So that kind of problem is what is considered a binomial setting, okay, or a binomial problem. binomial problems. Binomial problems have 4 characteristics, okay? And they are, we use the bins method to determine if something is a binomial problem. So the bins, the B, it's binary. By binary, we mean that it has 1 or 2 outcomes. Like it is, I have this or this can happen. I can have a success or I can have a failure. Okay? And basically I'm counting my successes or failures. Okay? Things have to be independent. All of his free throws are independent of one another. And he could either succeed at them or he could not. I have to have a set number of trials. So for instance, he had a set number of 3 trials. He had 3 possible shots. Okay, that's going to be my N. And then they all have to have the same probability. For him, that was his 0.72. Okay, because he was a 0.72 free throw shooter. So they have to be binary. There's success or there's failure. The events need to be independent, a set number of trials, and the same probability. Okay, when we're doing the problem, remember this is it looks like the probability of X equals K. Okay, and so what that ends up looking like in your calculator is NCR, okay, P to the X times 1 minus P, whoops, I forgot the 1, 1 minus P times N minus X. Okay, so again, looking at that, that's the total. N is our total. R, in this case, I know that's how it looks like in your calculator, but those are the X's, right? Those are the successes. So how many times would he make the free throw shot? The number of successes. P is my probability of success. So X is how many times I made those. 1 minus P is my probability of failure. Again, that's the binary part, the success or the failure, right? And then N minus X up here at the top, that would be my number of failures, right? My total minus my successes. Okay, all right, let's work through one more problem, and then we'll practice a lot more with this in class. Okay, so for each of the following situations, determine whether or not the given random variable has a binomial distribution. Justify your answer. So I'm shuffling a deck of cards. I turn over the top card. Put the card back in the deck and shuffle again. Repeat this process 10 times. Let X be the number of aces you observe. Okay, so our first part is the B for binary. Okay, is there a success and a failure? Okay, yes, there is. It's either an ace or it's not an ace. Right, so I have a success, which is an ace, a failure, which is not an ace. Are the events independent? Is each draw independent of the other? Yes, in this case, because I am putting the card back. I am replacing the card. Do I have an N set number of trials? Yes, I'm doing this 10 times. And is the probability of success the same every time? Yes, I have 4 possible aces. Every time I have 52 cards. All 4 of these things are my justification that yes, this is a binomial distribution. All right, let's look at the second one. Choose 5 students at random from your class. Let Y equal the number who are over 6 feet tall. Okay, so my B, is it binary? Do I have a success and a failure? Greater than 6 feet, that would be a success, right? Less than 6 feet would be a failure. So I have the binary part. Okay, are they independent? No, they are not. I have no replacement happening. I am not picking a student, putting them back, picking a student, putting them back. Right? So my probability is going to be changing every time. So this is not a binomial distribution. Okay, let's look at part number 2 then. Pedro drives the same route to work on Monday through Friday. His route includes 1 traffic light. According to the local traffic department, there's a 55% chance that the light will be red on a randomly selected workday. Suppose we choose 10 of Pedro's work days at random and let y equal the number of times that the light is red. Explain why y is a binomial random variable. Same thing we've been doing, right? He has a success or a failure, right? A success is it's a red light. A failure equals it's not red. So we've got the binary part. They are independent. He has a set number of times that he's looking at it, which is 10 of Pedro's work days. And the probability stays the same every time at 0.55. So that's my justification that this is a binomial situation. Now it says find the probability that the light is red on exactly 7 days. This is what you will be doing most of the time with binomial problems. And this will be the key to seeing how this will, being able to decide that it's a binomial problem, is you'll be basically counting how many successes out of a certain number, where geometric will be how many will it take until you get one success. This will be what is the probability you will get a certain number of successes. So, for instance, this would look like my probability of y equals 7. Okay, and so I've got 10 is my total number, C, 7 is my successes. I'm too close to the bottom and it's mushing up down here. Okay, so 10 is my total number, 7 is my number of successes. I'm going to multiply this by my probability of success, which is 0.55, to the power of success, which is 7. And then I'm going to multiply that by my probability of failure, which is 1 minus 0.55, and how many times it's going to fail, which would be 10 minus 7, my total number, minus my amount of times it failed. And that will give me 0.166. Okay, and so that's how we're going to do binomials, and we will practice them lots and lots.